In this video, we're going to again talk about potential energy, but we're going to take a slightly different approach to it, using differentials to define things rather than integrals. Right? Remember that when we defined the work in an earlier video, we said that that is equal to the line integral from some point A to some point B along the path of the force scalar with the differential displacement. And that's just a fine definition. It's perfectly okay, but and it has the advantage that it's intuitive. You can sort of see what's happening. You have a starting point and an ending point, and your particle is moving along, and at any one point you have a force that is acting on it, and the component of the force that's in the direction of motion is the one that changes its kinetic energy. That kind of makes sense. It is a little inconvenient, though, because it depends on multiple positions. It depends on the entire trajectory here. What you would like to have is a definition for work and for potential energy in the end that is only dependent on what happens in the neighborhood of a point, so that we can calculate what the potential energy is directly from the force without having to make reference to an integral. So to make that happen, what we're going to do is we're going to look at the displacement from some point R here to a closely neighboring point here at R plus dr. So this vector here is, displacement vector is dr. The work over this short distance then is just going to be f at r scalar dr. The integral goes away because we are integrating over such a short distance that the force can be taken to be a constant. This, of course, amounts to the same thing as fx dx plus fy dy plus fz dz. We can then also apply the Work-Energy Theorem, and that tells us that this work here is minus the change in potential energy, and it's a differential change in potential energy. Potential energy will depend on position, so we can just use then the chain rule, and we'll find that this equals now and you might recognize this as almost the gradient of u. In fact, what this is equal to is the gradient of u scalar dr. Right? So just to remind you, the gradient of u is just the vector du dx, du dy, and du dz. And if you take a scalar product of that with dr, which in this case is just dx dy dz, you get exactly what we have here. Okay, so we can then make the identification. Oh, there's a minus sign in front there too, very important. So we can then make the identification here directly that f of x is the u dx f of y is the u dy, f of z is the u dz, with minus signs in front. Let's not forget those. So this gives us, so this is now on component form, also comparing what we have over here to what we have over here. We'll find directly that the force equals minus the gradient of the potential energy. This is just the extension to 3 dimensions of what you saw in physics 2305, when you were told that the force was minus, so this was in 2305, that the force in the x direction is just minus du dx. This is not the same thing, but in 3 dimensions. Okay. So, just to get an intuitive feel for what this actually looks like, take a look at this topographic map. This is a map of Blacksburg, and you can see these lines here correspond to constant height, constant elevation, but also because, of course, the potential, the gravitational potential, equals mgh, these lines also correspond to constant potential energy. So here we have u, gravity is some constant, and this line corresponds to u grav being some other constant. These are equipotential lines. And you may recall that the gradient of a potential, or the gradient of any function, is going to be perpendicular to these lines. So it's going to point uphill. So if the gradient is large, it corresponds to a steep hill. Small gradient corresponds to a not so steep hill. So this is the gradient of u. What this formula says is that the force is in the opposite direction of the gradient. So that along these slopes here, the force of gravity is downward, which is what you'd expect, right? If this were a ski slope, if you point your skis downhill, then the force is acting to do positive work on you and your speed increases. If instead you face your skis uphill, then the opposite thing happens. Negative work is done on you and you slow down. So seen from that perspective, this definition should be relatively intuitive, I think. Although it will apply to any conservative force, not just gravity, of course. So much for the relationship between force and potential energy. The other thing that we want to cast in a differential form is not just this, it's also the expression for the work. Or specifically, the condition that tell us that a force is conservative. So, as we just recently mentioned, there are 2 conditions for a force to be conservative. It has to depend only on position, but also the work line integral is independent of path, which means that if you integrate around a loop, a closed loop, then the net work is going to be 0. Okay. This is not a differential formula. This is an integral formula. We found a differential formula for relating the force to the potential energy. We want to find something similar for this condition. And then we can do everything in terms of what happens in the neighborhood of a single point. So I'm going to state this mathematically as a theorem. And then we will at least loosely prove that theorem. So the condition that this work integral, is independent of the path from RA to RB is equivalent to the condition that the curl of F, the force F, is 0 everywhere. So then, of course, we can replace this condition with that condition. Right. So let's try and show this both that this independence implies this, and that this condition, curl equals 0, actually implies the path independence in both directions. So here's the proof. So we know that if this integral is path independent, then the force can be written as minus the gradient of some potential energy. If we then take the curl of the force, that's the same thing as taking the curl of the gradient of u. Now this is 0, which you should know. In case you don't know, I'll show rapidly here the proof of that, which is a privilege we have in an online video. So this part here is the gradient, and that's the curl. So what I did here was just relied on the condition that epsilon ijk is completely antisymmetric. I switch to indices, I get a plus sign. Then I just switch the definition of j and k. I should just mention the Einstein's summation convention applies here. I sum over I sum over j, I sum over k. So this is just a relabeling. I'm allowed to do that. So I've now shown that minus the curl of the gradient of u equals plus the curl of the gradient of u. The only way that can be possible is if that is 0. Okay. So we've shown that the curl of f is 0 if the force is conservative. So this proves the implication that in a conservative force, if you have a conservative force, then this is true. We now want to show the other thing, and that is that if this is true, that leads to a conservative force. So to do that, we will invoke Stokes Theorem. Stokes Theorem, if you remember, says that the integral, or if you've seen it, I'm not sure, but if you haven't, this is what it says. If you take the integral around some surface of a vector field, so here is the surface, and we're integrating around this, then that's the same thing as integrate across this surface of the curl of that vector field. Now I'm not going to prove Stokes' theorem, but if you haven't seen before, hopefully you can at least accept that it is reasonable. What it says really is that the microscopic rotation, that's what the curl measures, the microscopic rotation inside the field here, or inside the surface, if you sum it all up, then it equals the macroscopic rotation that you get if you go around the outside of the surface. That's really what the Stokes theorem says. So if that's true, that means that if this is true everywhere, then that means that the integral, of course, of the curl of f over any surface is going to be equal to the line integral around the circumference of that surface. And that's the work. But since this is 0, those things are both 0. So that proves the theorem in the other direction. That is that if this is true, then the path integral is path independent. Then the line integral is path independent. So to summarize, the two important things that we've said in this video are that the force equals minus the gradient of u, and that the curl of the force is equal to 0 everywhere is equivalent to the second condition of a force being conservative. So let's end this video with a brief example using this formula. What we want to do here is to show that the Coulomb force is conservative. So if you have two charges, Q and little q, there will be a force on the little charge FQ. Which is given by this formula, something you should already know. Now this is exactly analogous to the force of gravity, which we've already shown using the integral formula is conservative, or at least satisfies this this condition. We're now going to use this condition on this force here. But first I'm going to rewrite this as gamma times the vector r over r cubed. Gamma just contains kqqq, and the vector r over r cubed, I hope you can appreciate, is the same as r hat over r squared. The next step is then to calculate the curl, and since that's a vector, we'll look first at the x component. That should be obvious because the fz component of the r vector here, the z component of the r vector is just z. Using the chain rule. Now we know that r is given by this. And similarly, this then gives this. Just making the substitution here. The same thing over there. That's equal to 0, right? And we can do the same type of calculation for the x and for the y and z components. So in other words, we've shown that the curl of the Coulomb force is identically equal to 0 everywhere, which proves the path independence of the path integral, which is what we set out to do.